In the northern reaches of Japan, just outside the city of Chitose in Hokkaido, the landscape is defined by its quietude. Vast stretches of forest, heavy winter snowfalls, and the pristine waters of the Bibi River. For decades, this region was known for its natural beauty and its proximity to the new Chitose airport, a gateway for tourists seeking powder snow and hot springs. Today, however, the silence has been replaced by the rhythmic cacophony of pile drivers and the hum of heavy machinery. Here, amidst the subarctic chill, the Japanese state, in concert with a consortium of its most powerful corporations, is attempting to reverse the flow of history. This is the site of IIM-1, Innovative Integration for Manufacturing, the first fabrication plant of Rapidus Corporation. It is a structure that carries the weight of a nation's industrial soul. Rapidus is not merely a startup, it is a national project, a desperate and audacious bid to reclaim a title that Japan lost 30 years ago, the world's leader in semiconductor manufacturing. The stakes could not be higher. We stand at the precipice of the Angstrom Era, a new epoch in computing defined by the transition from nanometers to atomic-scale measurements. As artificial intelligence reshapes the global economy, the silicon chips that power these algorithms have become the most critical strategic resource on Earth, more valuable than oil, more contested than rare earth metals. Currently, the manufacture of these advanced logic chips is dangerously concentrated in Taiwan and South Korea, sitting on geopolitical fault lines that threaten to rupture the global supply chain. Japan's answer to this vulnerability is Rapidus. The company's goal is to mass-produce 2-nanometer logic chips by 2027. To understand the sheer scale of this ambition, one must realize that Japan's indigenous capability for logic chips, via manufacturers like Renesas, has long been stuck at the 40-nanometer node. While TSMC's recent JASM plant in Kumamoto brought 12 nanometers and 28 nanometers capability to Japanese soil in 2024, it remains a foreign-controlled entity focused on mature nodes. Rapidus intends to leapfrog these intermediate steps entirely. It is a moonshot that requires compressing decades of iterative learning into a 5-year sprint, fueled by trillions of yen in government subsidies and a critical alliance with American technology giant IBM. To appreciate the gravity of the Rapidus project, one must first look backward to the era when Japan was the undisputed king of silicon. In 1988, the landscape of the global semiconductor industry looked radically different than it does today. Japanese corporations commanded a staggering 50.3% share of the global market. Giants like NEC, Toshiba, Hitachi, Fujitsu, and Mitsubishi Electric were household names, not just for their consumer electronics, but for the chips inside them. They dominated the market for DRAM, dynamic random access memory, the workhorse memory chips required for the booming personal computer industry. During this period, Japan's manufacturing prowess was feared in Silicon Valley. The efficiency and yield rates of Japanese fabs forced American stalwarts like Intel to abandon the memory market entirely and pivot to microprocessors, a move that famously saved Intel but signaled the ceding of memory dominance to the East. The Japanese model was one of vertical integration, IDM, integrated device manufacturer, where companies designed, manufactured, and sold their own chips in their own devices. However, the 1990s brought a perfect storm that began the erosion of this empire. The United States, alarmed by Japan's technological ascendancy and the trade deficit, exerted immense political pressure, leading to trade agreements that handicapped Japanese exports. Simultaneously, the market began to shift. The rise of the PC required low-cost, standardized memory chips. New entrants from South Korea, Samsung, Hynix, and later Taiwan, focused relentlessly on cost-cutting and massive capital investment, undercutting Japanese pricing. As the 21st century dawned, the industry underwent a structural revolution that Japan failed to navigate, the rise of the foundry model. Spearheaded by TSMC, Taiwan Semiconductor Manufacturing Company, this model separated chip design, fabless, from chip manufacturing, foundry. Companies like Nvidia, Qualcomm, and Apple could focus solely on designing innovative architectures without the burden of operating billion-dollar factories. Japan's vertically integrated giants were too slow to adapt. They viewed manufacturing as a competitive advantage to be kept in-house, even as the capital requirements for new fabrication plants, fabs, skyrocketed. Burdened by legacy costs and a refusal to consolidate, their market share plummeted. By 2019, Japan's share of the global semiconductor market had withered to 10%. The nadir of this decline was the bankruptcy of Elpida Memory in 2012. Elpida was the last stand of Japan's DRAM industry, originally formed from the merger of NEC and Hitachi's memory divisions, and later absorbing Mitsubishi Electric's operations. Despite government rescue attempts, it could not withstand the price wars waged by Samsung and the rising yen. Elpida was acquired by Micron Technology of the US, symbolizing the final capitulation of Japan's memory dominance. In the wake of Elpida, Japan retreated to the supply chains upstream. It maintained a chokehold on critical materials, photoresists, etching gas, and equipment, Tokyo Electron, screen holdings. But it lost the process technology, the ability to actually build the advanced logic chips that serve as the brains of modern devices. While TSMC and Samsung raced toward 10 nanometers, 7 nanometers, and 5 nanometers, Japan's domestic logic capacity stagnated at 40 nanometers. This created a lost 15 years gap in manufacturing capability. The decision to establish Rapidus in 2022 was an acknowledgement that the market would not correct this imbalance on its own. It required state intervention to bridge the chasm between 40 nanometers and 2 nanometers. The disparity between Japan's existing infrastructure and the target set for Rapidus is difficult to overstate. In the semiconductor world, a node generation typically brings a 20 to 30% improvement in performance and efficiency. Manufacturers usually progress sequentially, for example, 7 nanometers to 5 nanometers to 3 nanometers, because each step requires mastering new physics and lithography techniques. The following table illustrates the node gap that Rapidus attempts to cross in a single strategic maneuver, contrasting the iterative progress of global leaders with Japan's stagnation. Rapidus is attempting to compress the learning curve of the FinFET era and the early EUV era into a single development cycle, moving directly to gate-all-around (GAA) architecture. This is akin to a nation that stopped building airplanes in the propeller era suddenly deciding to build a hypersonic stealth jet, skipping the jet engine era entirely. To understand why Rapidus is betting on 2 nanometers and why IBM is the partner of choice, we must delve into the physics of the transistor at the Angstrom scale. The term 2 nanometers is a marketing label, but it corresponds to a specific hard limit in semiconductor physics where the prevailing architecture, the FinFET, ceases to function effectively. For the past decade, the industry standard has been the FinFET, Fin Field Effect Transistor. In this design, the channel through which current flows is a vertical fin, and the gate wraps around it on 3 sides to control the current. This 3D structure allowed manufacturers to scale down from 22 nanometers to 3 nanometers. However, as the fin gets smaller, the gate loses the ability to fully pinch off the current, leading to leakage, electrons slipping through when the transistor is supposed to be off. This wastes power and generates heat. At the 2 nanometer node, the industry is shifting to a new architecture, gate-all-around (GAA) nanosheet transistors. In a GAA nanosheet design, the vertical fin is replaced by a stack of horizontal silicon sheets, nanosheets. The gate material completely surrounds these sheets, wrapping around all 4 sides. This provides superior electrostatic control. The gate can shut off the current with absolute precision, enabling the chip to operate at lower voltages without leakage. In May 2021, IBM Research unveiled the world's first 2 nanometer node chip, fabricated at its facility in Albany, New York. This test chip served as the proof of concept for the technology that Rapidus is now licensing. The specifications of this prototype define the target for the entire project. The IBM 2 nanometer architecture features a 3-stack nanosheet design. Each transistor consists of 3 horizontally stacked sheets of silicon, each approximately 40 nanometers wide and 5 nanometers high. The gate pitch, the distance between transistors, is 44 nanometers, and the gate length is 12 nanometers. The most headline-grabbing metric of this technology is its density. IBM claims the 2 nanometer process can fit 50 billion transistors onto a chip the size of a fingernail. Clarifications from technical analysis indicate that IBM defines a fingernail as approximately 150 square millimeters. This calculation results in a transistor density of 333 million transistors per square millimeter, MTR per millimeter squared. This density is not merely for bragging rights, it translates directly to performance and efficiency. IBM projects that chips built on this 2-nanometer node will achieve 45% higher performance or use 75% less energy than the 7-nanometer chips that were standard at the time of the announcement. For Rapidus, this technology is the magic bullet. By adopting GAA nanosheets immediately, they bypass the diminishing returns of the FinFET era and position themselves on the same architectural footing as TSMC's N2 and Samsung's SF2 nodes. The technological ambition of Rapidus is inseparable from the geopolitical anxiety of the 2020s. The COVID-19 pandemic exposed the fragility of global supply chains, while rising tensions between the United States and China fundamentally altered the calculus of semiconductor manufacturing. The concentration of advanced semiconductor manufacturing in Taiwan, specifically within TSMC, has become a singular point of failure for the global economy. With China's increasingly assertive posture toward Taiwan, policymakers in Washington and Tokyo realized that relying on an island that Beijing claims as its own for 90% of the world's advanced chips was an unacceptable strategic risk. In July 2022, the United States and Japan formally launched the Economic 2+2 framework. Involving the foreign and commerce/industry ministers of both nations, this dialogue prioritized economic security and supply chain resilience. The joint development of next-generation semiconductors became a flagship initiative of this alliance. For the United States, Rapidus represents a trusted alternative source of advanced logic, reducing reliance on Taiwan. For Japan, it represents a last chance to regain technological sovereignty and revitalize its hollowed-out electronics sector. As a METI official starkly put it, "The era where the world is at peace, and it doesn't matter who supplies our semiconductors, is over." Lacking the domestic R&D to develop 2-nanometer technology indigenously, Japan turned to its Western allies. In late 2022, the Japanese government orchestrated a dual-track strategy. Rapidus and the newly formed R&D organization, LSTC, Leading Edge Semiconductor Technology Center, announced a strategic partnership with IBM for the Gate-All-Around (GAA) transistor technology. Simultaneously, they signed a Memorandum of Cooperation (MOC) with IMEC, Belgium, the global hub for lithography research, to master the critical extreme ultraviolet (EUV) patterning processes. IBM and IMEC occupy unique positions in the industry. IBM is no longer a high-volume manufacturer. In 2014, it sold its semiconductor manufacturing division, including fabs in East Fishkill, New York, and Burlington, VT, to GlobalFoundries. In a deal that highlighted the brutal economics of chipmaking, IBM actually paid GlobalFoundries $1.5 billion to take the loss-making unit off its hands. However, IBM retained its jewel, the Albany Nanotech Complex. This research center remained a hotbed of innovation, developing the IP for 7 nanometers, 5 nanometers, and eventually 2-nanometer nodes. It is this IP that Rapidus, via LSTC, has licensed. The partnership involves a massive transfer of human knowledge. Rapidus has dispatched a cohort of approximately 100 to 150 engineers to the Albany Nanotech Complex. These are not fresh graduates. Many are seasoned veterans of Japan's semiconductor industry, with an average age closer to 50. They are engineers who worked during Japan's golden age, now tasked with absorbing the intricacies of GAA transistors from IBM and EUV lithography process flows, with support from IMEC. This alliance faced a significant legal threat in 2023. GlobalFoundries sued IBM, claiming that the technology IBM was sharing with Rapidus and Intel utilized trade secrets that GlobalFoundries had acquired in the 2014 sale of IBM's microelectronics division. GlobalFoundries argued that IBM had misappropriated this IP to set up competitors. The lawsuit cast a pall over the Rapidus project, raising fears of injunctions that could halt the technology transfer. IBM countersued, arguing GlobalFoundries had breached its contract by abandoning the development of 7-nanometer chips in 2018, leaving IBM without a supplier for its advanced server chips. The dispute highlighted the messy divorce of IBM's manufacturing past. As of 2025, the legal battle had ended. While the litigation created uncertainty, Rapidus and IBM have proceeded with the Albany training program and technology transfer, operating under the premise that their collaboration remains legally distinct from the specific IP claims in the New York dispute. While the legal and intellectual battles were fought in New York and Belgium, the physical reality of Rapidus is taking shape within the city of Chitose, Hokkaido. The site selection was strategic. Rapidus chose the Chitose BB World Industrial Park for IIM-1, Innovative Integration for Manufacturing, for three primary reasons. Water. The semiconductor manufacturing process is incredibly thirsty. Hokkaido offers abundant groundwater and industrial water resources crucial for the ultra-pure water systems, while the nearby BB River serves as a pristine environmental benchmark that the facility is designed to protect. Space. Unlike the dense industrial zones of Honshu, Hokkaido offers vast tracts of land for future expansion. Renewables. Hokkaido has a high potential for renewable energy, critical for the energy-intensive EUV processes. The construction of IIM-1 has proceeded at a pace that justifies the company's name. September 2023. Groundbreaking ceremony held. December 2024. The first EUV lithography tool from ASML was delivered and installed. This was a historic moment, marking the arrival of extreme ultraviolet lithography equipment for advanced logic mass production in Japan. April 2025. The pilot line became operational, and the first EUV exposure was successfully completed. July 2025. Rapidus announced the start of prototyping for 2 nanometer GAA transistors and confirmed that the wafers had achieved expected electrical characteristics. This timeline is aggressive even by industry standards. Installing over 200 pieces of advanced equipment and achieving functional prototypes in under 2 years from groundbreaking is a testament to the urgency driving the project. The facility utilizes the proprietary Rapidus Hybrid System, RHS, a construction method allowing simultaneous work on different floors to drastically shorten the schedule, along with sophisticated dampers to protect the sensitive EUV machinery from seismic activity, a constant threat in Japan. Building a fab is not enough. Rapidus needs a business model that differentiates it from the 800-pound gorilla, TSMC. TSMC's dominance is built on massive scale, tens of gigafabs churning out millions of wafers. Rapidus cannot win a volume war. Instead, Rapidus CEO Atsuyoshi Koike has articulated a strategy of high-mix, low-volume production. The company targets the specialized market for AI accelerators and edge computing chips, where customization and speed are more critical than raw cost per unit. To achieve this, Rapidus is pioneering the RUMS, Rapidus Unified Manufacturing Service model. The traditional semiconductor supply chain is fragmented horizontally. A fabless design company, like AMD, sends a design to a foundry, like TSMC, for front-end wafer fabrication. The finished wafers are then shipped to a different company, an OSAT like ASE, for back-end packaging and testing. This handoff introduces latency and feedback loops that can take weeks or months. RUMS integrates both processes under one roof. Rapidus aims to handle everything from wafer processing to advanced chiplet packaging. This vertical integration allows for design technology co-optimization, DTCO, where the manufacturing process is tweaked to suit the specific chip design, and vice versa. A key technical enabler of RUMS is the shift from batch processing to single wafer processing. In traditional fabs, wafers often travel in FOUPs, front-opening unified pods, containing 25 wafers. Certain steps, particularly thermal annealing and wet cleaning, are applied to all 25 at once in large furnaces or baths. If there is a defect or a variation, it affects the whole batch, and data is averaged across the lot. Rapidus plans to process wafers individually across the entire line. While this theoretically lowers total throughput, volume, it drastically increases velocity, speed. A single wafer can move through the factory faster without waiting for a batch to fill up. Furthermore, it allows for granular data collection on every single chip. This data is fed into AI models to optimize yields in real time. For a customer who needs a prototype or a small run of highly complex AI chips quickly, this speed advantage could be worth the premium price. Rapidus is entering a battlefield already occupied by titans. The race to 2 nanometers is a three-way struggle between TSMC, Samsung, and Rapidus, with Intel attempting to re-enter via its 18A node. TSMC remains the formidable leader. The Taiwanese giant began mass production of its N2, 2 nanometers technology in late 2025, with high-volume manufacturing ramping up throughout 2026. TSMC's N2 also uses nanosheet transistors, but it benefits from the company's massive existing ecosystem. TSMC has already secured the alpha customers, Apple and Nvidia, who drive the volumes necessary to depreciate the massive cost of 2 nanometer fabs. While rumors of delays to 2026 have circulated, TSMC's execution track record is vastly superior to its peers. Samsung Electronics provides a sobering warning for Rapidus. Samsung attempted to leapfrog TSMC by introducing GAA technology early at the 3 nanometer node, SF3E. However, this ambitious move was plagued by yield issues. Reports indicate that Samsung's 3 nanometer yields hovered around 10 to 20% for long periods, struggling to reach the break-even point. Samsung targets 2 nanometer mass production in 2025, but analyst skepticism remains high. If a conglomerate with Samsung's resources struggles to master GAA yields, the challenge for a startup like Rapidus is evident. The chart above illustrates the precarious timing of the Rapidus entry. By the time Rapidus achieves mass production in 2027, TSMC will likely be optimizing its N2P, performance enhanced, or N2X nodes. Rapidus will be arriving late to the party, necessitating a flawless execution of its service-oriented RUMS model to attract customers. Despite the impressive construction speed and the backing of the Japanese state, Rapidus faces an existential valley of death in the coming years. Semiconductor manufacturing is the most capital-intensive industry in human history. Revised estimates in late 2025 suggest Rapidus requires 7 trillion yen, approximately $48 billion, to reach full mass production. While the government has significantly increased its commitment, pledging nearly 3 trillion yen in cumulative subsidies by early 2026, the project still relies on a fragile mix of public funds and hesitant private capital. This discrepancy reveals a continued funding gap of several trillion yen. The founding companies have been hesitant to pour billions into a risky venture, preferring the government to shoulder the burden. While MITI has pledged support, private banks are cautious, haunted by the memory of Elpida's default. Without a clear path to profitability or a guaranteed major customer, raising the remaining capital remains the single biggest hurdle. Factories do not generate revenue. Customers do. TSMC has a line of customers waiting for its capacity. Rapidus has potential. The company has secured a partnership with Tenstorrent, the AI chip startup led by legendary architect Jim Keller. Keller, the mind behind chips at Apple, Tesla, and AMD, has praised the Rapidus strategy, stating that the industry needs an alternative to the TSMC monopoly. Tenstorrent plans to use Rapidus for its AI accelerators and high-performance RISC-V CPUs. However, Tenstorrent alone cannot fill a fab. Rapidus needs anchor tenants, companies like Google, Meta, or Amazon, who design their own silicon, to commit to the Japanese foundry. While Rapidus has flagged US firms as potential customers, no definitive high-volume contracts have been publicly confirmed beyond development partners. Finally, there is the physics. Creating a single functional 2 nanometer chip is a scientific triumph. Creating millions of them with a yield of 90% is an industrial miracle. The single wafer processing model is theoretically sound for speed, but unproven for high-volume yield learning. If Rapidus cannot stabilize its yields, the cost per chip will remain astronomically high, rendering it uncompetitive even for niche applications.